Hi class, welcome back to multivariable calculus. As promised, in this lecture we'll be doing a little bit of physics exploring motion, velocity, and acceleration. So we're going to continue go on with our parameterized functions. And in physics, the position vector is defined as follows. So we have a position, so it's going to be vector r, that's a function of time. So r of t, and it's going to be some function of time for the I hat component, a different function of time, so g of t for the j hat component, so the y component, and another function of time, some h of t for the k hat or the z component. And velocity is a rate of change with position. So if you're looking at the position vector, what you're doing is you're taking the first derivative of position with respect to time. So that would give you velocity, the rate of change in position. So velocity, so vector v of t, and I know this is a little confusing because we used vector v before to just show the direction. This v is the velocity vector, and it's equal to the first derivative of the position vector, so r prime of t. So what we'll have to do is we'll have to take the first derivative with respect to time of function f of t for the I hat component of velocity, and then the first derivative for the y hat component with respect to time, and then the same with h. And so these are full derivatives. These are derivatives with respect to time. So it would be dr over dt. Now, acceleration is the rate of change in velocity. So with acceleration, what we're doing is we're taking the derivative of velocity with respect to time, so the first derivative of velocity with respect to time, or we're taking the second derivative of position with respect to time. So this is going to be some acceleration. So vector a of t, so these are all vectors because they have these different x, y, z's components, I hat, j hat, k hat, unit vector in each of those directions, is equal to the first derivative of velocity, and then have the second derivative of position. Okay, so those are the different ways of defining acceleration. So the first derivative of velocity with respect to time and the second derivative of position with respect to time. And this is going to be f double prime of t for our I hat component plus g double prime of t for our j hat component plus h double prime of t for our k hat component. Now let's look at paths of motion. So one path of motion we can follow is uniform circular motion. So with uniform circular motion, the position vector with respect to time, so as a function of time, is going to be equal to r cosine omega t for the I hat component plus r sine omega t for the j hat component, where a period is defined as 2 pi divided by omega. So let's take a look at this. So we're looking at uniform circular motion for a circle with radius r. Okay, so this is going to be radius r. And we have uniform circular motion, so circle. And then looking at, so if I was to look at the velocity as we moved about, the magnitude of the velocity tangential to the direction of circular motion, the velocity is going to be equal to the magnitude of the angular velocity, which is omega, times the radius. That gives us the velocity. And the acceleration is going to be perpendicular to the velocity. Okay, so it's going to be pointing, it's going to be perpendicular to velocity, pointing inward towards the center of motion, so towards that center of our circle there. And so the magnitude of acceleration is going to be equal to the magnitude of velocity squared divided by radius. That's how that's defined if we're looking at circular motion. So the period is going to be 2 pi, right, which is the radians in a circle, divided by the angular velocity, gives us the period. And so that's going to be time, right? And then if we were going to look at the path of motion for a straight line, that would be the position vector. So r of t is going to be some initial position as a function of time. So this is similar to what we did last class, looking at looking at line segments and parameterized curves, plus some function of t times the direction vector, where the initial position, vector v, so the initial position, the velocity and acceleration are all parallel to one another and the line of motion. Now, if we wanted to go and figure out the distance traveled along a path from A to B, the way we'd calculate that, so distance is going to be equal to, we're going to integrate from point A to B along the path. You integrate the magnitude of velocity dt, right? Since the first derivative of position gives you velocity, if you want to get the total distance from one point to another, you have to integrate velocity to get that distance. So let's try out an exercise together. And suppose that the position vector r of t is equal to t squared I hat plus t cubed minus 2t j hat plus t squared minus 5t k hat. At what point does the particle pass through the xy plane is what we're trying to figure out. So we want to see when this passes through the xy plane, which means that that is where our z is 0 when we're passing through. Our z component has to be 0 when we're passing through the xy plane. And so that's going to be t squared minus 5t has to be 0 for that to happen. And so what we can do, and this is still going to, so let's try to pull out a t here to find the solutions. So that's equivalent to t times t minus 5. And so this tells us the particle will pass through the xy plane at t equals 0 and at t equal 5. And so then we have to figure out what the position is at these times, because we're looking for at what points does the particle pass through the xy plane. So we're going to have to look up at r of 0 is going to be equal to 0 I hat plus 0 j hat plus 0 k hat. So it's going to the particle is going to pass through the xy plane at 0, 0, 0. And then also we have to look at r of 5, which is going to be 5 squared I hat, which is 25, plus, so 5 cubed is 125, minus 2 times 5 is 10, j hat, plus, and then of course, this we already looked for, we were looking for when this was 0, this is 0, k hat. So it also passes through the xy plane at 25, 115, 0. So those are the 2 points. Okay, next we want to know what are its velocity, speed, and acceleration at these points that we just found. So first we need, in order to get the acceleration, the velocity, that's going to be the first derivative of position. So velocity, so velocity is going to be the first derivative of position, which is going to be 2t I hat plus 3t squared minus 2 j hat plus 2t minus 5 k hat. And the acceleration is going to be the first derivative of velocity, which is going to be 2 I hat plus 6t j hat plus 2 k hat. Okay, and so now let's find the velocity at 0. So for t equals 0, we'll do over here. So v of 0 is going to be 0 I hat minus 2 j hat minus 5 k hat. Okay, so that's the velocity. The speed is going to be the magnitude of velocity. So speed is going to be the square root of 2 squared plus 5 squared, so 4 plus 25. And that's going to be the square root of 29. Then the acceleration, we just plug into the next equation. So a of 0 is going to be 2I hat plus 0J hat plus 2K hat. Lastly, let's try now for t equals 5. So the velocity at t equals 5 is going to be 2 times 5, so 10I hat, plus 5 squared is 25, times 3 is 75, minus 2 is 73, j hat, plus 2 times 5 is 10, minus 5, plus 5k hat. Then to get the speed, we have to take the magnitude, or the distance, so the magnitude of velocity at t equals 5, and that's going to be equal to the square root of 10 squared, which is 100, plus 73 squared, which is 5,329, plus 5 squared, which is 25, and this gives us about 73.85. And then lastly, we need to find the acceleration at time 5. And this is going to be 2I hat plus 30J hat plus 2K hat. Okay, so we have found the velocity, speed, and acceleration of the points in part A, in the where these position vectors were. So this is when the particle passes through the xy plane. So this is how the velocity when the particle passes through the xy plane at 0, 0, 0, and this would be the velocity when it passes through at 25, 15, 0. This would be the speed it's traveling, and then we also have the acceleration. All right, let's do one final problem together. And in this problem, a shell is fired from ground level with an initial speed of 480 feet per second at an elevation angle of 30 degrees. So there's a bunch of stuff we need to find. The first thing is a vector function and parametric equation of the shell's trajectory. So let's just look at what's going on here. So we're firing a shell from ground level. Okay, and here's y, and here's x. And so we're firing from ground level at an initial speed of 480 feet per second and an elevation angle of 30 degrees. So what's going to happen is it's going to arc, and then it's going to eventually drop back down to the ground surface. So when initially we shot it at an angle of 30 degrees. That's that elevation angle there, and we know what the initial speed is. So we're given the initial speed, and speed is the magnitude of velocity. So we know the magnitude of velocity, and this is initial, so this would be at time 0. And that is equal to, so if we think about, so we're just dealing with x and y here. We're only working in 2 dimensions. And remember our equation for velocity, that velocity, right, is equal to the first derivative of position, which is going to be some f prime of t I hat plus another function of t, g prime of t, j hat. That's what we're working with here. And so we know that the velocity is going to, the magnitude of velocity, or this initial speed here, is going to be some function, first derivative of some function of time from the position squared plus some g prime of t squared, and that's going to be 480. We're given that, 480 feet per second. So we also know that the initial position is going to be 0. So that's 0 I hat plus 0 j hat plus 0 k hat. And so the initial velocity, so these knots, initial, that just means that time is 0 there. So v, the velocity, is going to be, so what we need to do to get the velocity from the speed is, well, we can find the components of the velocity because we know the magnitude and we know the angle that the shell was fired at. So to get the initial velocity, we're going to take the magnitude, or the speed, and to get the x component with the 30 degrees taken from the x relative to the x, we're going to have cosine 30 degrees I hat, so that's our x component, plus 480 sine 30 degrees j hat. So there's our y component. Okay, so now we end up getting that our initial velocity is going to be equal to 240 times the square root of 3 I hat, right? Because cosine 30, if you remember, is the square root of 3 over 2, plus sine of 30 is just going to be 1/2, so 240 j hat. And from there, we can continue on, and we know actually the acceleration. So here we're dealing with feet per second, so we're dealing with English units. And the thing is, acceleration is going to be acting on the shell just downward. It's going to be the acceleration due to gravity. So A of t, and if you don't know this one off the top of your head, the acceleration due to gravity in English units is about 32 feet per second per second. So the acceleration is going to be minus 32 j hat, and that's because the acceleration is the acceleration due to gravity. Okay, and so now we know the initial velocity, we know the acceleration, so let's just try to find the velocity. So in order to find the velocity as a function of time, it's going to be equal to the initial velocity vector and plus, so if you integrate acceleration, you get velocity. So it's going to be our initial velocity plus our acceleration, the integral of our acceleration dt. Because remember, if you integrate, technically, you're going to have, you integrate acceleration, you get velocity plus a constant, and that constant is actually the initial velocity. So that's where that comes in. And so our velocity is going to be equal to, well, we have our x component, which is going to be 240 times the square root of 3 I hat. And for acceleration, that only has a j component. So then we're going to add on to that 240, which was from our initial velocity. And if we integrate minus 32 dt, we get minus 32t. Minus 32t. And that's going to give us j hat. Okay, so our velocity as a function of time is going to be 240 times the square root of 3 I hat plus 240 minus 32t j hat. All right, we're almost there. We just need to find the parametric equation for the shell's trajectory. So now we're just looking for r of t. And r of t is going to be equal to the integral of our velocity. So this is going to be equal to 240 times the square root of 3t I hat plus 240 t minus 16t squared j hat. Okay, and so this would be x of t, this would be our function for y of t. So this would be our f of t, for example, this piece right here. And this piece down here would be our g of t. All right, so that is that part. Box around it. Next, we need to find the max altitude. So to find the max altitude, the max altitude is going to occur when dy over dt is 0. So when we have a slope of 0. Okay, so we're going to get our max elevation or altitude, our max y, when dy dt equals 0. So we can also think of this as our x of t, and this is our y of t. So if we look at our y of t, that is going to be 240 t minus 16t squared. If we look at our derivative, y prime t, dy dt, right? That is going to be our 240 minus 32t. And when this is 0, we get the time for our max altitude. So if we solve for t, we get t equals 7.5 seconds. And so now that we know the time that the max altitude occurred, we can go back through and plug in 7.5 for time into our y of t, and that'll give us the max altitude. So y of 7.5 is going to be 240 times 7.5 minus 16 times 7.5 squared. And so our max altitude is going to be 900 feet. So that's our answer for B. And I'm sorry I did not leave very much room on the slide here. Okay, so now let's look at the shell's range. So the shell's range is the difference in the distance along the x from the start point and the end point. So you'll notice for the shell's range, at each of these points, that's when y is 0. So the altitude is 0. So for the shell's range, we have y of t is equal to 0. So for that, what we're going to have to do is using y of t, so t times 240 minus 16t, so that's our 240t minus 16 squared is equal to 0. And now we have to solve for the 2 times that y is 0. And of course, you can just eyeball and know that yes, the initial position, since we started at y equals 0, is one point at which y of t is 0, so t equals 0. And also, then we're going to have 240 equals 16t, which gives us t equals 15. Okay, so we know that y of 0 is 0. And so now for x, also x of 0 is 0. So to get the range here, we only need to look at x of 15 because we started at 0, because it's the difference between the two to get the total range. So x of 15 then is going to be plugging into this x portion of our position. So it's going to be 240 times the square root of 3 times t. So it's going to be 240 times the square root of 3 times 15. And this is going to give us 6,235.4 feet. And whenever you're dealing with problems like this, it's very important to include units. So on any quiz, any exam, make sure you include units. And now one more bit. We want to know the speed of impact. And so we've already determined that the time of impact is t equals 15 seconds. Okay, and so the speed of impact is going to be the magnitude of velocity at 15 seconds. Okay, so we just need to plug in 15 for our velocity, and we need to get the magnitude. So looking at our velocity vector, we have 240 times the square root of 3, and there's no t attached to that, so that's just going to be 240 times the square root of 3 squared, plus, now looking at the y component, it's going to be 240 minus 32 times 15. And this is going to give us the square root of 2,000, the square root of 229,825, which is going to be 479.4 feet per second. So not very different from our initial speed. It's not slowed down much when it hits ground, when it impacts. All right. Well, that was it for this lecture, and next time we'll be getting into looking more at vector fields, and so I will see you next time. Take care.